Okay, let's unpack this. We usually spend our time on this deep dive talking about data security.
Hmm.
How to stop a malicious hacker, how to encrypt data, or how to build these digital fortresses to keep information safe from intentional threats.
Right, from a human adversary.
Exactly. But today, we are shifting gears completely. We're moving away from that human threat model.
We are, and it's a crucial pivot
Yeah.
because we are facing a far more pervasive, natural, and utterly relentless enemy, noise. It's the
Noise.
constant underlying entropy of the universe,
Yeah.
just applied to digital communications.
I love that framing. We're talking about the crackle, the static, the thermal fluctuations, the electromagnetic interference,
Right.
the inevitable physical corruption that causes bits to flip. Whether your signal is traveling across a copper wire, a crowded Wi-Fi spectrum, or hurtling billions of miles through deep space.
And this is the realm of channel coding and error correction.
Right.
Exactly. So the listener sent us some fascinating source material covering the fundamental geometry and the linear algebraic machinery that makes robust data transmission possible, even over the absolute worst channels.
Okay.
Our mission today is to extract not just what these codes are, but to deeply understand the profound mathematical elegance that allows us to solve this seemingly impossible problem of bits tipping over on an inherently unreliable physical channel.
And if you're listening to this thinking, wait, how can you possibly fix something if you don't even know precisely what broke or where or when?
Mhm.
You are asking the central question that channel coding answers.
And the answer is found in one brilliant concept: redundancy.
Redundancy.
We knowingly and systematically inject more data than is strictly necessary. But this isn't random padding. This extra information is cleverly calculated. It's what allows the receiver to detect that an error occurred and, crucially, automatically repair that damage locally without ever having to, pause the transmission and ask for a resend.
It's self-healing data.
It is. It transforms unreliable input into reliable output.
Let's start by defining the core scenario that engineers face every single day. It's simple, yet the problem is enormous.
It is.
Data goes in, say, a short critical sequence of bits. It passes through the physical channel. Noise happens. A single zero might become a one or vice versa.
Yep.
Damage data comes out. We need a way to shout alarm if something went wrong, and ideally fix the damage and just move on.
To address the simplest form of that challenge, just sounding the alarm, we begin with a concept that is truly foundational to modern computing, something used everywhere, even in basic memory checks.
The parity code.
The parity
The
code.
single parity bit. It's so simple, it feels almost too primitive for this deep dive, but I mean, its elegance lies in its minimal cost.
The mechanism is perfectly straightforward, and it's our first taste of structured redundancy. You take your data vector, your payload of ones and zeros, and you append a single extra bit to it. This extra bit, the parity bit, is chosen such that the total sum of all the ones in the resulting sequence is 0 when calculated modulo 2.
Right. For those unfamiliar with modulo 2 arithmetic, it's just binary addition without carrying. But in this context, it just means we are concerned only with parity, right? Is the count of ones even or odd?
That's all it is.
If our data has an even count of ones, we append a 0. If it has an odd count, we append a 1. The overall final goal is always to ensure the tally of ones in the complete block is even.
And this minimal addition provides immediate, robust functionality against the most common form of error, the single-bit flip.
Okay.
If just one bit flips during transmission, and it doesn't matter if it's a data bit or the parity bit itself, the total sum of ones changes state. An even count becomes odd.
Oh.
The receiver performs the exact same check, sees the sum is now 1, modulo 2, and knows immediately. Aha, an error has occurred.
So, it achieves perfect detection of a single error. The alarm is triggered, and the receiving system can throw away the corrupted block and request a retransmission, or at least signal that the data is unreliable.
That's its strength. But we must immediately confront its major limitation, which is the whole reason we need more advanced codes.
Right.
As the source material points out, the parity code detects that an error occurred, but it provides no useful information on where the error is located.
Nothing.
It offers 0 diagnostic power, only a binary yes-no on integrity.
And worse, it fails completely if 2 errors occur simultaneously.
Exactly.
If the first bit flips and the third bit flips, the 2 errors just cancel each other out in the parity count. The number of ones remains even.
Exactly. A double error is an example of a silent error. The receiver checks the parity, sees an even count, and assumes the data is pristine when in reality it is fundamentally corrupted.
And for mission-critical systems, silent errors are absolutely unacceptable.
Totally unacceptable. We need mechanisms that can handle multiple bit flips without masking the damage.
You know, that structural concept, the simple check digit based on a calculation, has roots far outside of pure digital computing. It's been used for decades to ensure human reliability.
Oh, here's where it gets really interesting, showing how mathematical checks are essential for data integrity across disciplines. Think about the ISBN, the International Standard Book Number, printed on the back of a book.
Right.
That last digit, often separated by a hyphen, isn't just a part of the number.
It's a check digit.
It's a check digit, and it's far more sophisticated than binary parity. The historical ISBN system used a check digit calculated using a weighted sum of the previous 9 digits, calculated modulo 11.
Modulo 11. Why 11?
That choice of modulo 11, instead of, say, modulo 2 or 10, is the engineering brilliance. If you or a clerk mistypes one of the 10 leading digits, the final checksum won't match, and the error is detected. That's detection power.
But the real reason they use modulo 11 and a weighted sum is that it is sophisticated enough to detect the most common human typing error.
Transposition?
The transposition of 2 adjacent digits, swapping a 5 and a 6, for example.
Yep. Simple modulo 10 checksums often fail to catch transpositions because the total sum can remain the same. The modulo 11 system ensures that if you accidentally swap 2 digits, the check digit still signals an error.
That's a perfect example of designing the redundancy mechanism specifically to defeat the most probable failure mode.
Whether that failure is random noise or a slip of a human finger, yes.
But both the parity code and the ISBN check digit ultimately only provide detection.
Right.
If we want to move past detection and achieve true correction, the ability to fix the bits automatically, we need to increase the redundancy significantly.
Oh, yeah. We must move from minimal overhead to brute force, at least initially, to understand the mechanism of correction.
Which brings us to the triple rep code, the simplest example of a truly correcting code.
Instead of sending 1 bit, we send 3. If you want to transmit a 0, you transmit 1000. To send the 1, you transmit 111.
This code cost us 200% overhead just to send a single bit.
A huge cost.
But the gain is significant. The decision rule at the receiver is completely intuitive, relying on the majority rule.
Right.
If the receiver gets the sequence 010, they look at the group of 3, 2 zeros, 1 1. The majority dictates that the original signal must have been 0 new.
And this simple high-cost code can reliably handle a single bit flip. If the sender transmits 111 and 101 arise, the majority vote corrects the error back to 111.
So we have achieved both detection and correction of a single error.
We have.
So we've demonstrated that correction is possible, but only at an enormous cost in bandwidth. We've moved from just sounding the alarm to actually performing surgery on the data stream, but we're using a very inefficient scalpel.
Like very blunt instrument.
So the engineering challenge becomes, can we achieve the self-healing ability with dramatically less wasted bandwidth?
And to answer that, we need to formalize the problem. We need to stop thinking of these codes as ad hoc tricks like the majority rule and define them structurally using precise mathematical language. We need to define what makes a sequence legal.
So how do we formalize that dictionary of legal code words?
We introduce the concept of a block code, usually denoted with a C. And this is not a complex definition. It just states that a code of length nullers is simply a specific, carefully chosen subset of all possible bit sequences of length.
That subset is critical. If we are sending 7-bit code words, the total space has $2,707, so 128 possibilities. But our dictionary, C, might only contain 16 legal code words.
For example, yes, if we are encoding 4 data bits.
Right.
Think of this set C as our dictionary, the list of words we are allowed to use.
Right.
If we were using 26 letters, there are billions of possible letter combinations, but only a small fraction are valid, recognizable words in the English dictionary.
And those valid words are legal code words. The rest is just mathematical nonsense.
Exactly. The vast majority of sequences are mathematical gibberish, meaning they must be the result of corruption.
And the structural definition immediately links back to error detection. If the received word, let's call it dollars, is not in our dictionary, not in the set C, then we know with certainty that an error happened.
Yes. And the job of the engineer is to design that dictionary C such that even when noise corrupts the word, the corrupted word lands closer to the original legal word than to any other legal word.
Which brings us squarely into the realm of geometry.
Exactly.
To successfully engineer that dictionary C, Where corrupted words always point back to their origin, we need a mathematical ruler. We have to have a way to quantify the difference between the legal word we sent and the corrupted word we received.
Mm-hmm.
How robust a code is depends entirely on this measurement of difference.
We need a measure of distance in this abstract code space, and that is where the seminal concept of the Hamming distance, or delta, comes in. This was formulated by Richard Hamming back in the 1950s.
It sounds like a deep mathematical concept, but the mechanism is, well, it's profoundly intuitive. It's just counting differences.
Precisely. The Hamming distance between any two-bit vectors, $6 and 9, is nothing more than the count of the number of positions where the two vectors disagree. If $6 is 100, 100, and 1, 1, it's $1,100. They differ the second position and the fifth position. So the Hamming distance is 2. We say delta xy equals 2, 2.
So when we send a valid code word $6 and receive YAR, the Hamming distance delta x is the exact number of bit flips that occurred in the channel. It's quantifying the damage.
Yes, and it is crucial that the source material confirms this measure is a true metric. It satisfies the properties of non-negativity, symmetry, and, most importantly, the triangle inequality.
Okay.
This means it behaves exactly like physical distance in geometry, making it the perfect tool for measuring difference in the code space.
So let's visualize the error space. We send 6 alas, we receive yis.
The decoding problem simplifies entirely based on this geometry. Number 1, error detection. If the distance delta x is greater than 0 and yis is not in the dictionary C, we detect the error.
Simple enough.
Number 2, error correction. We assume the error that occurred was the smallest possible error. Therefore, we correct the received word AS to the legal code word $6 narrow, only if the latter is closer to 6 than it is to any other legal code word in the dictionary C.
We're dealing with geometric proximity in a digital space. This naturally leads to the concept of the error space around a valid code word.
We define the sphere concept. Wine S-ec. Think of Sempers as the center of a sphere and $5 as its radius, which represents the maximum number of errors we want to correct.
Okay.
This sphere contains every single word that differs from $6 by at most $5 positions. These are all the possible corruptions of $6 that are correctable.
So if our code is designed to correct, say, 5R1 error, the sphere of radius 1 around the original code word $6 contains the original $6 itself, plus all the corrupted versions that have exactly 1 bit flipped.
And if the received word lands inside that sphere of radius dollars, we use the correction rule. We pull it back to the center $6. That is the mathematical principle of maximum likelihood decoding. You choose the closest possible valid code word.
This raises the single most important structural question for any code designer. How far apart do the code words have to be for our spheres to work? If the spheres are too close, they overlap, and we run into that dangerous ambiguity we mentioned earlier.
That minimum separation is the critical structural requirement. We define the minimum distance as the Hamming distance between the two closest legal code words in our entire dictionary C. This DAD dictates the power and reliability of the code.
Okay, let's break down the mathematical conditions that link to the error capacity.
First, the condition for 5-liar detection. To reliably detect 5-liar errors, the minimum distance between any two valid code words must be at least $5 plus $1.
I want to pause on that $5 plus $. This is a point where engineers cannot compromise. Why can't the distance be exactly $5?
Imagine two code words, $7 and $62, that are exactly $5 distance apart. If we send $7 and the channel causes an error of size dollars, it is mathematically possible that this error maps $7 directly onto $6 foolish show. The receiver would receive sex by 2 and 2 blies, check its dictionary, see that $6 and $2 is perfectly valid, and assume incorrectly that no error occurred. The error remains silent.
Right. Or it just thinks $6 and $2 was the intended message.
Exactly. To guarantee that a note error always lands outside of the dictionary, we need a buffer of at least one position. Hence, 5 lies plus $.
That makes perfect sense. The gap must be wider than the maximum error you are protecting against. If we revisit the simple parity code, we found its null line is 2. Since $2 is 1 plus 1, 1, it reliably detects 1 to force the overlon error.
Now, for 5 error correction, the requirement is far more stringent. We need to guarantee the non-overlap rule. The spheres of radius dollar around every valid code word must be completely disjoint.
If they overlap, we have ambiguity. A received word yelling in that intersection region would be equally close to two different valid code words, say $6 and $6.
And the decoder can't decide. Correction is impossible. So to prevent the spheres from touching, the distance between their centers, must be greater than the sum of their radii, 5 to plus f there. Therefore, the geometric necessity forces the mathematical requirement. must be greater than or equal to $2 plus 1.
That is the algebraic heart of error correction. It ties the abstract concept of distance directly to the engineering capacity of the code.
And let's apply this crucial rule to the triple rep code, 1111. The Hamming distance between them is 3.
It is.
Since 333 and $3 at 2 plus another, the code reliably corrects $100 error. The spheres of radius 1 around 1,000 and 1111 do not touch. Everything inside the 1,000 sphere corrects back to 1,000 and vice versa.
So let's challenge that rule. What if an engineer tried to design a code to correct $1 on error, but only managed to achieve $1 of dollars?
If the dollar's only 2, the spheres of radius 1 would overlap entirely. If you have $6 and $6 only 2 steps apart, the word that's 1 step away from $6 is also 1 step away from $6.
Ambiguity is guaranteed.
Guaranteed. The decoder cannot correct, it can only detect.
So we cannot have ambiguity. This geometric understanding is fundamental. We are literally designing digital structures by measuring the minimal gap between them in the code space.
But here we hit the reality of engineering. We can't just keep adding redundancy endlessly to make the gaps wider and wider.
Right.
The engineer's goal is to maximize the amount of useful data, we'll call it dollars, while maintaining the required minimum distance within a fixed block length, no dollars.
That sounds like the classic resource constraint problem. We want the most information density possible for the protection we gain.
And there is a hard mathematical ceiling on what is achievable, formalized by the Hamming bound. It uses the geometric analogy of packing.
Okay, let's really unpack that analogy. Oranges in a box.
Right. Our box is the entire code space consisting of all 200 possible sequences of length, no dollars. Our oranges are the error correction spheres, each centered on a valid code word and having a radius $5.
And the volume of each sphere, the number of unique sequences it contains, is determined by that correction radius, $5.
Exactly. For a code length, not a dollar, the number of words in a sphere of radius $, is given by a formula involving binomial coefficients. Let's just call it V. That V is the volume taken up by one code word plus all its correctable, corrupted versions.
The Hamming bound, then, is a simple statement about limits.
It states that the total volume taken up by all the non-overlapping spheres must be less than or equal to the total size of the space, mathematically. Calculate 2 now.
If you violate this, your spheres must overlap.
And correction is impossible.
This is fascinating because it dictates real-world engineering choices before the designer even begins. If I decide I need to encode HK04 bits I, and I need to correct 5 LS2 errors, I can immediately calculate the minimum block lengths that I must use to satisfy this inequality.
It sets the non-negotiable theoretical limit on efficiency. If a code satisfies the Hamming bound with equality, meaning the spheres exactly fill the entire code space without overlapping and without leaving any gaps.
Like perfect tiling.
Perfect tiling? That code is designated a perfect code. They are exceptionally rare and mathematically beautiful, and the 7-4 Hamming code we are about to discuss is one of them.
Okay, so we've established the geometry, the need for distance, the non-overlap rule, and the absolute limit on packing density. But we still haven't solved the computational problem of the dictionary.
We need to move from lists and lookup tables to fast, structured computation.
Storing a dictionary of code words works for our tiny triple rep example, but once we scale up to modern data sizes, gigabytes of compressed video, or high-speed fiber data streams, relying on a lookup table to check for validity is computationally impossible and far too slow. We need a way to mathematically generate the correct redundancy and verify the incoming data at network speed.
And this brings us to the innovation of linear codes, which shifted channel coding from tedious geometry into the realm of powerful, fast algebra.
We're moving from the geometry of spheres to the algebra of matrices.
Exactly. These codes don't rely on brute force memorization. They rely on linear algebra over the finite field of 2 elements, math BBF22.
Which just means the only numbers we use are 0 and 1, and every arithmetic operation is performed modulo 2.
Right, which fundamentally means addition is just the XOR operation. $1 plus 1 is long.
And that simple mathematical structure is what makes linear codes so efficient in digital systems. Every step, every calculation is native to the hardware.
Yes. Instead of storing massive lists, we define the code using 2 primary small matrices.
Let's tackle the first phase, encoding. That's the job of the generator matrix.
The generator matrix is what creates our dictionary on the fly. It's a kel times in matrix, where $2 is the number of data bits and $, is the final code word length.
Okay.
We take our actual data vector, $6, and multiply it by DO daler. So the resulting code word 2 is guaranteed to be a valid legal word in our code, our HAL.
And since the dollars is a matrix of zeros and ones, and the calculation is modulo 2, this matrix multiplication is just a series of XOR operations.
Very fast XOR operations.
Yeah.
The beauty of linear algebra is that $dollar generates a set of code words. Governed dollars that is mathematically closed, meaning if you take any two code words from XOR them, the result is always another valid code word in $.
The source material highlighted that dollar usually has a specific structure. It contains the identity matrix.
That structure is known as systematic form, and it's an engineering choice for practicality. Dollars is partitioned into two sections: the identity matrix, IK-dollars, and a smaller matrix dollars.
Okay.
The identity matrix ensures that the original data bits are copied directly into the first part of the code word. The matrix dollars, then, is responsible solely for calculating the necessary redundant parity bits based on linear combinations of the data bits.
So it separates the payload from the protection.
Exactly. So dollar handles the creation of the redundancy. But once the word is corrupted in the channel, what diagnostic tool do we use? That is the profound utility of the parity check matrix. This matrix is the core tool for the receiver, designed to verify the validity of the received word. It is constructed such that if $R is a valid correct code word, then $$ multiplied by the transpose of $, must equal the zero vector. Tell it CT equals CDOS.
This is the mathematical signature of a legal code word. Any sequence generated by dollar sits in the null space of dollars.
Precisely. $$ defines the code space, and $$ defines the space orthogonal to it. They are mathematically linked.
So the receiver takes the incoming vector, which we know might be damaged, and multiplies it by dollars, the moment the result is non-zero.
The alarm goes off, and that resulting non-zero vector is the syndrome. It's typically a much shorter vector than the original code word, carrying the diagnostic information.
What's fascinating here is the analogy to medicine, where the syndrome is the symptom pointing toward the error. It is the signature that tells us something happened, and critically, it must contain information about what happened. Otherwise, it's just a parity code in disguise.
That insight, that the syndrome should be leveraged to pinpoint the error, is the genius behind codes like the Hamming code.
Yeah.
If the syndrome is 0, we trust the message and move on. If it is non-zero, the decoder needs to find the smallest possible error vector, let's call it $, that could have created that specific syndrome.
And small as possible means the error vector that has the fewest ones corresponding to the fewest bit flips.
Assuming that a single flip is exponentially more likely than 2 and 2 more likely than 3.
Right.
The decoding strategy, therefore, becomes a problem of matching the observed syndrome to the most probable error vector, Miller. Once $$ is found, we use the fact that the received word is the correct word plus the error. So we calculate the correct word by taking the received word and adding the error.
Which in modulo 2 is just another XOR.
Just another XOR. This whole process moves decoding from searching a massive dictionary, which is incredibly complex, to simply solving a matrix equation, which is vastly, vastly faster.
Okay, so this efficiency allows us to formally introduce the perfect example of this structure, the 7-4 Hamming code.
Invented by Richard Hamming while working at Bell Labs, frustrated by the error-prone computer systems of the time, this code takes 84 data bits and encodes them into 177 code bits. It uses 3 parity bits.
It's highly efficient. 3 redundant bits provide perfect single error correction among 4 information bits. It achieves maximum possible efficiency for single error correction given that block length.
It meets the Hamming bound with equality. It's a perfect code.
The gold standard for small block codes.
And the beauty of this code is in the construction of its dollar matrix, which is designed specifically to make the syndrome calculation a perfect GPS map.
This is the segment I've been waiting for. We are going to walk through the elegance of the Hamming code math, step by step, showing how the syndrome acts not just as a warning, but as a perfect mathematical index that pinpoints the error location.
This is where the abstract linear algebra becomes physically and operationally useful.
So let's define our components for the 7-4 Hamming code. We have K44 data bits, 1 CD7 code word length, and 3 check bits.
All right, so the parity check matrix dollars must have 3 rows and 7 columns.
And the crucial construction rule for the dollar matrix of a single error correcting Hamming code is simple yet revolutionary. Its columns are all the unique non-zero vectors of length 3.
Precisely. There are 23 $1 to 77 unique non-zero column vectors of length 3. Since our code word has 7 positions, we make sure that the columns of the dollar are simply those 7 unique vectors. We order them according to the error positions they will diagnose.
Okay, let's start with our data. We are sending a 4-bit message. Sex equals is 1111 mul.
Step 1. Encoding. We multiply this message $6 by the $4 times 77 generator matrix $2. Because the dollars is in systematic form, the resulting code word 7 will have the data bits 1, $1, followed by 3 calculated check bits.
Okay.
For this specific $6, let's just assume the correct pristine 7-bit code word $7 is 11110101010.
Now the channel gets involved.
Step 2, the channel error. We simulate a typical single-bit error. The source tells us the third bit flips. The third bit in $7 is a $1. It turns into a 0.
So the sent word $60 becomes the received damaged vector, let's call it tilde-sic, which is $1, 1 math B 0, 1, $0. The receiver knows the incoming sequence is supposed to be legal, but it only has tilde-sic.
And the knowledge of the code structure. So step 3, calculating the syndrome. The receiver immediately performs the diagnostic test. It takes the received damaged vector tilde and multiplies it by the transpose of $.
Okay, mathematically, why does this calculation give us a meaningful syndrome?
Remember that the received vector tilde is the sum of the correct code word CO and an error vector 2.
Right.
And the it is a vector of length 7 with a 1 only in a third position.
So $1, 0, 0, 0.
Exactly. When we multiply by $, the syndrome's all is equal to CDO, C plus ET, which is DDO CT plus H to go D2.
And since sin is a valid code word, we establish that stido tuos must be 0.
Precisely. That term vanishes. Therefore, the syndrome sigma is purely the result of the error vector EP2, caller H2082.
So the calculation for the syndrome is just $ multiplied by a vector that is mostly zeros, except for a single 1 at the third position.
And matrix multiplication tells us exactly what that result will be. Multiplying the dollars by an error vector of 50 me $, with a 1 naps at position $, results in the output vector being exactly the ith column of dollars.
That is the real magic. The syndrome is not just an arbitrary number, it is mathematically guaranteed to be identical to the column of dollars corresponding to the error location.
So let's assume the dollar matrix is constructed with its columns ordered from binary 1 to binary 7.
Okay.
The receiver performs the calculation, the dollars versus HET dollars T. Since the error occurred at position 3, the resulting syndrome dollars must be the third column of 3.
And the third column of H would be the binary representation of 3.
Right. Let's say the matrix is set up so the third column is $2, $1, or $1. The calculation yields the vector $2, $1. This is the non-zero syndrome alarm. But more importantly, we know what $1, $1 means.
This is the binary number 3.
It is. The syndrome vector is an index pointer, a binary GPS coordinate for the broken bit. Conclusion. The error must have happened at position 3.
That's perfect diagnosis. The syndrome has transformed the problem from a probabilistic guess, where is the error, into an algebraic certainty. The error is precisely at the position corresponding to this column.
Step 4. Correction. The receiver now knows the received bit at position 3 is wrong. It flips that third bit back, changing the 0 back to a 1, restoring the original code word C0.
And the original message, $1, $1, 0, is perfectly restored without any need for retransmission or human intervention.
Exactly.
What stands out to you about this structural shift? We have moved from the conceptual geometry of distance to a practical, implementable algorithm.
The incredible efficiency stands out. Compare it to the triple rep code, which needed 200% overhead
3 bits to send 1 bit.
to achieve $1, 1 correction. The 7-4 Hamming code uses 3 redundant bits to protect 4 data bits, an overhead of only 75%, and performs a far more sophisticated matrix-based diagnosis.
This is how mathematics enables practical, high-speed, reliable communication.
And think about the scalability. For a larger block, say a $15 SAML Hamming code, you are protecting 11 data bits with only 4 check bits.
4 check bits.
The 4 check bits generate 242111 equals 15 phi unique non-zero syndromes, capable of pointing to an error in any of the 15 positions. The diagnostic power grows exponentially with the number of check bits.
And this reliance on linear structure allows communication to proceed across highly unreliable channels, from the edge of the solar system to fiber connections susceptible to environmental noise, with the integrity of the data guaranteed by matrix multiplication.
Making reliable digital systems out of inherently unreliable physical components.
But I want to introduce a point of friction here. We've focused on the elegance of the single error correcting Hamming code. When Hamming designed this, he assumed noise was light.
Right, random and sparse.
What happens in a genuinely noisy environment like deep space or old magnetic storage, where errors often come in bursts, hitting 2 or 3 adjacent bits?
That is the code's limitation. If 2 errors occur in the Hamming 4, the 2 errors combine to create a resulting syndrome 7. However, that resulting Zallers will inevitably match the column of some other position, let's call it pickallers.
Oh.
The decoder, assuming only a single error is possible, will misdiagnose the location and flip the wrong bit.
So a double error leads to a miscorrection, corrupting the data even further.
Exactly. The syndrome approach assumes the shortest distance error vector, $2 is the correct one. If a 2-bit error occurs, its Hamming distance is 2, but the decoder might find a 1-bit error that generates the same syndrome.
And it chooses the distance 1 error.
It does. It flips the wrong bit, and the resulting word is now distance 3 from the original. This is why the Dibble 2f+1 rule is a strict requirement for a guarantee of correction.
So moving to burst correction correcting 1F22 or 433.3 errors requires massively increasing and thus massively increasing the number of unique syndromes we need.
And therefore, dramatically increasing the redundancy again. To correct 2 errors, you need 55 ounds. Achieving that means the code words are so far apart that the spheres of radius 2 around them cannot touch.
Which is a much harder packing problem.
Much harder. This typically forces the designer to look beyond standard Hamming codes and move into more complex polynomial-based codes like BCH or Reed-Solomon codes, which still rely on the fundamental geometry and algebra we've discussed, but leverage even more sophisticated mathematical structures to handle bursts.
Okay.
If we connect this to the bigger picture, the story of error correction is really the story of efficiency. We have moved from the primitive, inefficient majority vote of the triple rep code, which uses 200% redundancy, to the highly structured, matrix-based system of linear codes. Here, the minimum distance dictates capability, and the resulting error acts as a mathematical index, telling the system precisely where to apply the fix, often using less than 100% redundancy.
The beauty is that this mathematics is the bridge between the messy physical reality of the universe, the static and the noise, and the need for perfect, logical digital systems. It's an example of how abstract algebraic structure provides an incredibly robust foundation for modern engineering.
And the reliability of nearly all digital communication you rely on daily, from your phone calls to your satellite navigation, is underpinned by these matrices and the simple, elegant power of the Hamming distance.
And since we analyzed codes that reliably correct $1 error, achieving that mid-and-no, let's leave you with a final thought for your own exploration. We established that correcting 2 errors requires a minimum distance of 5,5, what mathematical adjustment would need to be made to the generator and parity check agidal matrices to achieve this 5 ball. Specifically, how would that increase and constrain the number of rows in the line, so the length of the syndrome, and how much longer would the block length dollar have to be before the Hamming bound even allowed for a 2-error correcting code to be practically designed?
That's a great question to think about.
Something for you to mull or explore on your own?